right, so we are starting out with Unit 12, and to begin, we are going to start looking at our strong acids. If you remember, with your definition of strong, it means that it dissociates completely. So while each of these acids has been written as a compound with a formula, they actually do not exist like that in water. The moment that any of these acids encounters water, it will immediately turn into its ions, and there will be no compound left behind. In your strong acid list, there are these 6, starting with your halogen family. You have your hydrochloric acid, your hydrobromic acid, your hydroiodic acid, and then 3 oxyacids, which are the nitric, sulfuric, and perchloric acids. With your bases, we end up having a total of 8 that we consider strong bases. Those 8 come from your group 1 ions, so lithium, sodium, potassium, rubidium, and cesium ions, all make strong bases. And then from group 2, your calcium ions, strontium, and barium ions are each able to accept 2 hydroxides to their formula. Again, remember, if we just use our calcium as an example, when it encounters water, you are going to go to 100% ion. So in this case, our calcium ion is actually going to release 2 hydroxides into the solution. That's the first thing to remember as we start reviewing our acids. This again is coming out of Unit 3. As we go above, let's also just refresh our memories about how acids taste. They're sour. So anything that is citric, anything that has candy, all of those things that are Sour Patch Kids or Warheads, all of those include some sort of acid. Bases, on the other hand, are bitter. And we do some cooking with bases, such as baking soda, as well as endives or other lettuces, all of which are bitter. That's going to include your spinach. It's also going to include things like Brussels sprouts. Acids will feel very sticky to the touch, which is why if you get a bunch of orange juice all over, it's hard to get cleaned up. While bases are going to be feeling slippery, as if you've somehow rubbed yourself down with a whole bunch of soap. Litmus paper is something that we don't use very often, but when it comes to acids, they are considered to be red when litmus paper touches them. So it's a form of an indicator which identifies that the acid has some sort of pH that is below 7. With your bases, litmus paper will turn the color of blue. And again, that's going to indicate that you have some sort of pH that's above 7, somewhere in the range of 7 to maybe even 14. That's why we have our acids listed as red, and we have our bases right now listed as blue. Phenolphthalein is another great indicator, and you may remember using this when you happen to do a titration. When phenolphthalein encounters an acid, it is clear, and it remains clear. When it encounters a base, it turns pink. Okay, so having said all of that, we start out by, again, remembering the various definitions. Let's start out with the Arrhenius model. Again, the Arrhenius model is going to be the most basic model that we work with. When it comes to the Arrhenius model, the thing that you would be looking for an acid is that somehow there are hydrogen ions in solution. So when you place that acid into the water, hydrogen ions come out and dissociate. That therefore means, if you remember, hydrogen and hydronium, the H3O plus ion, happen to be very similar and pretty much we consider them identical. On the bases, if you were looking at an Arrhenius model, the hydroxide ion must be present in solution. Now, as I'm looking at this, I realize that I wrote basic next to Arrhenius. I mean simplest form. Okay, so the simplest way of telling if it's an acid or a base is going to be, does it start with a hydrogen ion? Because that will end up in solution. Does it end with a hydroxide ion? Because that will end up in solution. All right, we also have our concentrations. And our concentrations can either be very dilute, meaning there are not a lot of particles in solution, or it could go all the way up to concentrated, meaning there are a number of particles in solution. When it comes to our strong acids and our strong bases, we know that for every one acid that is dissociated, exactly one hydrogen ion will come off, and exactly one negative anion will come off. That means that if I have a 0.1 molarity of HCl, I'm actually going to have a 0.1 molarity of H+, as well as a 0.1 molarity of Cl-. If I'm looking at one of my bases, let's again pick a nice strong base. So barium hydroxide. Again, when we put that into solution, in this case, for every barium ion that dissociates off of our barium hydroxide, we will obtain 2 hydroxide ions. That means if again I have a 0.1 molar barium hydroxide solution, a 1-to-1 ratio will give me 0.1 molar barium ions. But a 2-to-1 solution will give me a 0.2 molar of hydroxide ions. That therefore means that the barium hydroxide solution, even though it began as the same concentration, will have a higher concentration of the basic ion, hydroxide, than the same 0.1 molar HCl solution has of the hydrogen ions in solution. Oops. All right, next what we're going to be doing is using that idea on the next page with our values of pH. When it comes to pH, you do want to remember that hydrogen and hydroxide are sharing in the water solution. So when we look at our water dissociating, we want to remind ourselves that that water is actually creating an equilibrium. And it is the equilibrium of this water that actually creates our pH and our pOH values. So if we look at the K, and this would be the Kc for water, we can see that there are going to be hydrogen ions, which again is the same as hydronium, multiplied by the hydroxide. Now remember, that means that water is not going to be part of our K expression, and that's because water is in fact a liquid. When you're looking in at the water, it does not dissociate very much. And so we know that the dissociation constant at 25 degrees Celsius is always going to be 1.0 times 10 to the negative 14th. Because that is the case, we also know that any time you have pure water at 25 degrees Celsius, you're going to end up with a concentration of 1.0 times 10 to the negative 7th. That's because we'll get 1 hydrogen for every 1 hydroxide, which is really x times x. So the square root of 10 to the negative 14th happens to be 10 to the negative 7th. Because we know that this is a constant, and because we use it quite a bit, we call that value the Kw. So rather than labeling it Kc for a very generic equilibrium constant, we label it Kw for specifically the water dissociation constant. That therefore means that when you look at the pH scale or the pOH scale, if you have pure water, you should be at a value of 7 on either scale. That value is going to represent neutral. When you are looking at the pH scale, anything that is below that 7 is going to end up being acidic. And while we normally say that the pH scale can go down to maybe 1, maybe 0, it actually could go down a little bit lower than that, depending on how strongly concentrated your acid is and how strong the actual acid is. When it comes to the bases on the pH scale, they're going to be considered anything above 7. And again, a base is going to be supposedly stopping at the number 14, but it could go a little bit beyond that, again, depending on concentration as well as strength. The pOH scale is going to be the exact same concept, but in an opposite scale. That means that values on the pOH scale, because you would be looking at the concentration of the hydroxide ion, will have values that are less than a 7. And values that are greater than a 7, going up to a pOH of, say, 14, would be considered acidic. So these are two ways of just looking at how your acids and your bases work. As we go to calculating the pH, as you may have already seen, you do have some information there that's pretty useful. First off, we use what's called a box, meaning that you can travel the perimeter of anywhere along the box, but you cannot go through the box. With the box, you can have your pH, your pOH, you can calculate your hydrogen ion concentration, and since I want that concentration to be in molarity, I'm going to go ahead and put it in brackets, and your hydroxide ion concentration. Again, you want that to be in molarity, so I'm going to put that in brackets. With that information, what it then means is that you can calculate between them. The hydrogen to hydroxide relationship is really based on Kw. So if you want to know any information about hydrogen or hydroxide, and you have one of the concentrations, then you can plug into the Kw expression with that concentration and solve for the other. At the same time, the pH and pOH are related by addition. When they add together, you might have already guessed that they had to add up to be 14. When you want to calculate from pOH to OH minus concentration, or vice versa, you want to keep in mind that there are two types. Now I know that you guys are using quite a bit of NSolve, but just to make sure you have the right idea, if you want the pOH and you have the hydroxide ion concentration, then you can take the negative log of that concentration to get to the value. At the same time, if you have the pOH but you want the concentration, then what you'll need to do is take the anti-log, or rather 10 raised to the negative pOH, and that will then get you the concentration. The same is true for pH and H+'s concentration. If you're hoping to get the pH, but you know the concentration, plug it into the negative log. And again, if that happens to be the hydronium ion concentration, no problem. If you know the pH instead, but you want to solve for the hydrogen ion concentration, you're going to take that and plug it in as an exponent of 10 raised to the negative pH value. So again, you can travel from pH to pOH, from pOH to OH minus, from OH minus even to H+, all the way around the box. You cannot, however, take, for instance, hydrogen ion concentrations and immediately get a pOH, or vice versa. You can't cross through the box. We're going to start out with some simple examples, and these examples are with strong acids only. So if we take, strong acids or strong bases only. If we take a look, we're just going to go ahead with this. Calculate the pH of a typical adult blood. We happen to know the hydrogen ion concentration, so that therefore means that the pH value is going to be equivalent to the negative log of the hydrogen ion. Check to make sure that your hydrogen ion is in fact in molarity, because it does need to be molarity, and then you can very simply plug it in. When you solve, you should get a value of 7.4. And you can see then that that means that your pH concentration, your pH value is going to be just slightly basic. And blood actually turns out to be slightly basic. The other thing that you're going to want to watch for will in fact be significant figures. If you take a look, there are 2 significant figures in your concentration. Because there are 2 significant figures in your concentration, after having solved for your pH value, you're going to want to have 2 decimal places. So 2 sig figs in your concentration gives you 2 decimal places for your pH. All right, let's take a look at the next one. In the next example, we have pure hydrochloric acid. So if you remember, hydrochloric acid is going to dissociate 100%. When you sit down and you write that, that therefore means that if you know that this is a 0.056 molarity, it's a 1-to-1 ratio. So all of it will turn into hydrogen ions and chloride ions. Clearly, not all of it is useful for your calculation. There is no chloride used in the calculation of pH. That means the only thing we want to focus on are the hydrogen ions. You're going to go ahead and take the negative log of those hydrogen ions, and when you do so, you'll see that what you get is the pH. This then means that our pH value is going to be a 1.25. As you then go and solve for the pOH, remember that the 2 of the values added together will add up to give you the value 14. So now you can just subtract 1.25 from 14, and that's going to represent your pOH. What's that? 12.75. And regardless which way you go, you're going to end up again with 2 values meaning the exact same thing. A low pH means acidic. A high pOH is still acidic. Again, notice that I did sneak in there the fact that as I'm looking at my number, I had 2 significant figures. And because I had 2 significant figures in my concentration, I have 2 decimal places. All right, let's take a look at the next one. We're now working with a strong base. And again, I've selected the barium hydroxide. Again, remember that when you're working with the barium hydroxide, the entire compound is going to dissociate into its ions. That's barium ions and, of course, hydroxide ions. For every 1 barium hydroxide you get, remember, you'll get 2 hydroxide ions. So as we look at our barium hydroxide concentration, it's 0.0009604 molar. Again, barium is a 1-to-1 ratio with that formula. So that's going to also be 0.0009604 molar. On the other hand, the hydroxide ion is going to be twice that value because there are 2 hydroxides in the formula. Therefore, when you go to solve for the logs, the easiest one to go to is first going to be the pOH. And when you plug that in, you want to remember to plug in twice that value, which is 0.001 9. Hold on, I'm totally cheating. 19208, sorry. Okay, as you plug that in, again, you're going to calculate. And when you go to calculate, you're going to get 2.7165, I think. All right, that's what I thought it said. Because again, I'm looking. All right, so notice this time, as you look at it, your concentration in this example now has a total of 5 significant figures, which means I technically need 5 decimal places. So I need 1 more, so hold on. Okay, I am missing the number 2. All right, so now 5 significant figures in your concentration gives you 5 decimal places on your pH. All right, if you're going to solve for POH, what am I talking about? If you're going to solve for pH, go right on ahead and subtract from 14. I do not have a calculator in front of me anymore, so make that happen. That ends our first video for Unit 12, and there's another one on its way.